All right, great. So before I get started, thank you everybody for joining us. I have the usual few announcements. First of all, the CSAFE All Hands meeting is going to be held in May 2022 next year. We have the dates. It's hard to change these dates. And again, we'll be on the campus of Iowa State. More than welcome if you would like to participate. Next week, November 1st and 2nd, there's a workshop at Carnegie Mellon University. It is going to be on blind testing at crime labs. And I am sure that if you contact Bill Eddy, he'll be happy to tell you how to sign up. We have a couple of webinars coming up. November 28th, Simon Cole from University of California, Irvine is going to be talking about probabilistic reporting in American criminal cases baseline study. And then on December 13th, we have Keith Einman from California State East Bay, and the topic will be announced later. So please make sure that you join us for those seminars. So today I'll talk about learning algorithms for evaluating forensic glass evidence, and this was So-Young Park's, part of So-Young Park's, she's sitting right there, part of So-Young Park's PhD dissertation, and so the work is largely hers. The acknowledgements before we get started, Peter Weiss from BKA has been fantastically generous. He was the first person to share some data with us so that we could get started. And he has always been available to answer questions. And he even sent us the German standards so that we could use in our measurements. Joan Buscaglia and Tatiana Trejos have been two people that we have contacted for information. Thank you so much. We have created a database of glass fragments. I'll call it the ISU database of glass fragments that can be loaded free from this GitHub address that I give over there. In that address, you will find not only the data that we're going to be using in this study, but also all the code that we wrote, the description of the analytical methods that we use for the data. I think that's about what you're going to find. If you have any questions about the data, feel free to contact us. All the measurements that we're going to be using were obtained using, or all the measurements that we uploaded into this database were obtained by Dr. David Peat. He is a geochemist at the University of Iowa, and the instrumentation and the methods he used were laser ablation, inductively coupled plasma mass spectrometry. I should point out that this work is not funded by NIST. This work for us, TRACE, is out of scope. So we used my own endowment to fund this work. I have a president's chair in statistics at IOSU that has a very generous endowment, and that's what we have used to do this work. So there's a lot of literature implicit in what I'm going to be talking about. Sometimes I cite, sometimes I don't. But since these slides are going to be posted, you get the list of papers that I'm going to be referring to here and there. That's the first part. This is the second part. The last paper that I list over there is a joint publication with So-Young that was recently accepted for publication in the Annals of Applied Statistics. All right, so here's the outline for the talk. Setting up the problem, then I'll talk a little bit about the data sources we had to work with. Discuss the current standards, which are the interpretation methods that are recommended in the ASTM E2330 and ASTM E2927. The alternative approach we propose, comparison of the different approaches, and a few final thoughts. Okay, so I'll go very fast over this because I assume that I'm preaching to the choir and everybody knows about glass. So when there's a crime and a glass object is broken, then it may happen that small fragments transfer to the perpetrator. And so the one question of interest is, do those fragments at the crime scene and on the perpetrator have a common source? So that's one question. And two related questions to that are the following. First of all, how similar are the fragments on the suspect and obtained from the broken glass at the crime scene? But then we also need to ask ourselves, if we find that these two fragments or these fragments are similar, how typical would that degree of similarity be among fragments that perhaps came from different sources? So is the similarity significant or is it not? So very briefly, glass is made by melting together sand, soda ash, dolomite, limestone, and sodium sulfate at very high temperatures. Manufacturers, when add to the mix cullet, which is just recycled broken glass. And what happens is all of this stuff is melted at very high temperatures in this ginormous furnace. The molten glass is extruded from this furnace in the form of a white ribbon. And this ribbon travels over a bed of molten tin that provides a very smooth surface for the glass. And as it goes down, travels down this line, it starts cooling, it cools down slowly. Eventually, it gets cut and processed for transportation. I actually went and visited a glass manufacturing plant, and it was really very impressive. This ribbon, the ribbon of glass, is about, I don't know, 5 football fields long. It's just enormous. So that was a very interesting experience. This is a schematic that we obtained from Tangram Technologies. There is the furnace, the molten glass, the float area. There's annealing chamber where the glass is cooled slowly to prevent the buildup of stress, inspection, and cutting and storage. So, hello, okay. So what are the properties of glass? Well, there's several types of properties. Physical properties like color, thickness, type of coating. Optical properties like the refractive index of the glass. Chemical properties, the concentration of various elements in glass. Physical properties are not, well, sometimes are used in forensic examinations if the samples that the forensic examiner has to work with are large enough. Optical properties, the refractive index used to be used to discriminate glass from different sources, but with improved manufacturing methods, the refractive index is very uniform, so there's no big differences like there used to be. And so most of the, I think today most of the interest is on looking at the chemical at the concentration of different elements in glass. There's many different ways to measure elemental concentrations. The one that we focus on here today is LA-ICP-MS. You can obtain concentrations for 40, 50 different elements. Typically in forensic work, we use about 18 of those elements. So the elements that I will be working with today are all of those that are listed up there. I think I know the name of most all of them, but don't ask me just in case. As I said, the method for measuring these concentrations is LA-ICP-MS, and the details regarding the instrument, the calibration of the instruments, and all of those technical details are in a README file in the GitHub repository for the ISU data. So other data that we had available were the data that was generously provided by Peter Weiss and his collaborators. This is the Bundeskriminalamt database. This one consists of the one that we used in this work is the following. There's 62 samples of float glass with different origin, different countries, different manufacturers, different everything. One fragment per sample was analyzed, and there's 6 replicate measurements for each one of those fragments. The other piece of information we got from Weiss is this one pane that was obtained in some store in Virginia. It was analyzed at the FBI, I believe. And there were 34 fragments obtained from this one pane. Each one was replicated 6 times. One of those fragments was measured on 11 consecutive days, as a matter of fact. I should say that I'm limiting everything to architectural float glass. So this is exactly one type of glass and nothing else. Jose Almiral and his collaborators collected another database that is also publicly available. This one, I think it's was published around 2002. In terms of architectural float glass, there's 112 samples. They all have different origins, different date of manufacture. Again, there's only 1 fragment per sample and 3 replicate measurements. The problem with this data is that not all the elements that are in the BKA data are also in the FIU data. So there's 14 elements in common out of the 18 elements that were used in the BKA database. We modeled ours after the BKA database. So what we obtained was 31 samples of glass from a manufacturer that I'm going to call A, and 17 samples of glass from a manufacturer that I'm going to call B. There was a design in this study. So for example, manufacturer A gave us a sample of glass about every day for a period of 3 weeks. And what we obtained was a sample from the left end of the ribbon, a sample from the middle of the ribbon, and a sample from the right end of the ribbon. We didn't use the middle samples at all. And so for each day, we have 2 samples of glass, 1 from the left and 1 from the right end of the ribbon. For manufacturer B, the design is pretty much the same, except that the data were collected over 2 weeks. We took 24 randomly selected fragments per pane of glass, and 21 of those fragments were measured 5 times, so we have 5 replicates. 3 of the 24 fragments was replicated 20 times. So the idea here is that we have 18 elements that we know are dependent. And so we wanted to have enough measurements to allow estimation of the measurement error covariance matrix. So we have 3 fragments per pane that have 20 replicates that allows that estimation. The within pane between fragment covariance matrix. And we can do that because we have 24 fragments per pane. And then, of course, the between fragment covariance matrix. In the case of manufacturer B, we only have 17 samples. For manufacturer A, we have 31. So in our database, there's a total of 1,152 fragments and a total of almost 8,000 measurement vectors. Each measurement vector has 18 dimensions. And we have the same elements as in the BKA data. The plan is to continue adding to this data. And if you would like to add to this data, if any of you out there has data that you would like to see added to this database, we would be happy to curate it and accept it. So why do we need so much data, and why do we need so many fragments per pane, and so on and so forth? We need that because there is a very complex dependence structure between the concentrations of different elements in glass. I am showing you there are 2 correlation matrices. The left one is from one of our panes. The right one is from that one pane measured multiple times from the BKA data set. The elements are not in the same order because we clustered so that we could get all the negative correlations in one corner, and so on. But you can see immediately, for example, that in our data, some elements they have some strong negative correlations. There's nothing like that happening in the BKA sample. And so to think that we can get 2 or 3 panes and estimate a covariance matrix that will apply to every pane is fanciful. there's a lot of data that we're going to have to collect before we can characterize the variability within and between pains more or less successfully. There's obviously some signal when you look at the concentrations of different elements in fragments, in pairs of fragments that are known to come from the same pane of glass and fragments that are known to come from different panes of glass. Here I just picked 8 of the elements at random, and if you focus on titanium, for example, this one on the top, the blue distribution simply represents the histogram of differences in titanium concentration among fragments that are known to come from different panes of glass. And the red here denotes the difference in the concentrations of fragments that are known to come from the same source of glass. And so as you can see, there's a difference in the distributions, right, across elements when fragments come from the same source or from different source. But in none of these cases, no single element would allow you to discriminate between sources, although, you know, you'd think if we combine all this information, maybe we can do something with it. So there definitely is some signal in the chemical elemental concentrations. The question is how to make good use of them. This is just looking at, so what I'm showing you here is panes ordered by production date. And these box plots represent the variability across fragments within the same pane. And so what we can see here, this is sodium, for example. We can see that overall the concentration of sodium in company A and in company B and in the BKA data on the average is pretty similar. And it doesn't seem to vary in any systematic fashion by day of production. But there's a lot of variability within pain. So so these box plots show that there's quite a variability across fragments within the same pain. Titanium is pretty constant in company A, pretty constant, but very different in company B, and very different yet in the BKA data. Zirconium is interesting. In company A, there's a clear time trend, and so at least during the period where we observed the glass, it went down pretty clearly, then it stabilized. Doesn't change in company B. Hafnium, which is highly correlated with zirconium, has the same pattern as zirconium. So how do we analyze and interpret? So that was a very, very simple exploration of these data. I should say that Sam Tyner and So-Young Park, 2 of the postdocs in CSAFE, and I are working on more in-depth exploration of this data right now. You can do too, since you have the data available now. So there's 3 different types of approaches to analyze and interpret glass data. One of the standards are 2 interval-based methods. These are univariate in the sense that they look at one element at a time. There's an approach that was proposed in Weiss et al. In 2011, and a similar approach proposed by Trejos et al. In 2013. The Trejos et al. Approach is what is recommended in the 2 ASTM standards that talk about measurement and interpretation of glass elemental concentrations. Over the years, there have been some parametric approaches, multivariate, meaning they take all the take at least a collection of those elements into account at the same time. This is pretty old. In 1968, Parker and Holford proposed this one approach that works reasonably well. Jim Curran has done a lot of work on glass, so I just list a few of the publications. If you go to our paper, there's a whole lot more references. And then what I'll call non-parametric, also multivariate approaches. Zadora was a pioneer in this. There's an interesting method for classifying glass into different categories: architectural float, automobile, this and this and that, in a publication in 2009. And So-Young Park and myself in 2018 used this approach to see whether we could answer the same source, different source question. Okay, so what do these interval methods do? So again, proceeding one element at a time, this is what the ASTM standard says one should do. First, obtain 3 replicate measurements from at least 3 fragments from the known source at the crime scene, and however many fragments one has from the, however many question fragments one may have. Using those K fragments, we compute the mean concentration for each element and the standard deviation of the concentration, and construct an interval, which is the mean plus minus 4. And normally it would be plus minus 4 standard deviations. In this case, there's a minimum value that the standard deviation can take. So if the standard deviation is below 3% of the mean, then instead of using that calculated standard deviation, we use a value equal to 3% of the mean. And so the idea goes as follows. If I compute 18 of these intervals, and then I compare the mean concentration in Q relative to those 18 intervals, we conclude that if the concentrations in Q fall inside the corresponding intervals for all elements, then we declare Q to be indistinguishable from the known source. And so the minute that one of those concentrations falls outside, we declare them to be distinguishable, I suppose. So these methods have a few good attributes, but several limitations. The good attributes is that, of course, it's super easy to implement, and it doesn't depend on external reference population data. So you're just working with case data. Now, this is a blessing and a curse because typically there's very little data that are available when one has only the case data to work with. And furthermore, because this approach relies only on casework measurements, it does not address, in fact, it doesn't permit addressing the second part of the source question, which is the significance of the similarity between the known and the question samples. The approach is statistically inefficient in the sense that it ignores dependencies among the elements, and it has this sort of undesirable property, which is that when the noise in the measurements increases, in other words, when the standard deviation, the variability between fragments in the known source increases, these intervals become wider, and therefore the chance of concluding that Q sample is indistinguishable from K also increases, and this is counterintuitive. So one can, this is not interesting, but one can express this interval-based criterion as a score. So for each element, we can calculate a score the way it is set here. And then the overall score then that we call S of S sub ASTM is just the maximum of these element-wise scores. And the decision rule here would be the following. If the score is less than or equal to 4, then the samples are indistinguishable. And if it's above 4, if it's above 4, then the samples are considered different. So there's a different version of this algorithm proposed in Weiss et al. What they did is, instead of computing the standard deviation from the measurements at hand, they proposed using a fixed relative standard deviation that they computed from 90 measurements. I think it's 6 replicates each, of elemental concentrations obtained from the German standard DGG1. And again, they have the same floor in the relative standard deviation. So if for any element the relative standard deviation is below 3% of the mean, then the relative standard deviation is equal to 3% of the mean. And so in this particular case, we only use the mean concentrations from the casework data. So what we propose is a completely different approach. We propose using what's called supervised learning algorithms. And the general idea is the following. So we will also develop a score that quantifies the similarity between two fragments of glass. And then what we'll do is the following. We'll suppose that we have a large and representative, whatever that may mean, sample of glass fragments, and we use our score to compare all possible pairs of fragments from this database. And so if there's any justice in this world, and if the method is worth anything, well, we might find something like what I have in this figure, that when you have known mates, so when you have pairs of fragments that are known to come from the same pane of glass, then the distribution of score values you get is perhaps something that looks like this black one. And when you have pairs of fragments that are known to come from different panes of glass, maybe when you compute those similarity scores, you get something that looks like the gray distribution. And so if that's the case, and you're, let's suppose you have these reference score distributions. Now, if you are an examiner yourself, then what would you do? So you would compute the similarity score for your pair of known and question fragments. This would help answer the question, how similar are these two fragments? And then you would take that score that you just computed and compare that score to the reference score distributions. And that would let you figure out whether the score you obtained is a typical value if samples have a common source, or maybe it is a typical value if samples have a different source. And so that would sort of help you estimate some sort of an empirical probability of same source, different source. I should say that this approach is pretty close to what FR-Stats uses in the case of fingerprints, and what the Hare, Hoffman, and Karikiri algorithm uses to classify bullets. Okay, so what are the advantages of this type of learning algorithms? Good. So first of all, you can quantify the degree of similarity between two fragments. Second, because in principle you can develop these distributions of scores for known mates and known non-mates, you can calculate what we might call the probative value of the evidence. So the probability of observing a score under each one of the two competing hypotheses. That means you can even compute some error rates, and depending on how you define those error rates. Once these algorithms are trained, the algorithm can be used to compare any pair of fragments as long as the new pairs of fragments are of the same type as the fragments that were used to train the data. And so if you have, a reference database of architectural flow class, you cannot use the algorithm you develop for those to compare container fragments or something to that effect. And these are statistically appealing because they exploit dependencies across elemental concentrations in effective ways. So what are the limitations? I mean, this is not all wonderful. So the algorithms are pretty good and allow you to classify items into different classes well, but only when you have good training data. So the performance of the algorithm is critically dependent on your training data. The approach is kind of like a black box, so you don't really know what's going on when you are producing the score. It's not clear what we mean by reference population of non-mated pairs, so one has to think about what one means by non-mated pairs, and I'll talk a little bit more about this afterwards. And whenever new measurements become available, the algorithm needs to be trained on the updated data. So if this were ever to be used in practice, one imagines that maybe every year one would add more measurements to the reference population, would retrain the algorithms, and you know, for the next year use those retrained algorithms until the next update or something like that. Okay, so how do these algorithms work? Very simple. First of all, we have to have a database, this training data for which we know ground truth. So, so we have, in the case of glass, we have a bunch of pairs of fragments that we know come from the same pane of glass, and a bunch of pairs of fragments that we know come from different panes of glass. And then we tell the algorithm which features it should be looking at. And I'll say in a minute what a feature is, which features it should be looking at to see if it can associate values of these features to fragments that have a common source, and then different values of the features when fragments have a different source. And so once this algorithm is trained, meaning once the algorithm says, oh yeah, if two fragments have a common source, the values of the features are typically this values, then I can present the algorithm with a new pair of fragments that is not in the training data set, and the algorithm looks at the features and then determines whether that corresponding arrangement of features suggests that the fragments have a common source or not. So what do we mean by features? Features is anything you decide. These are measurements that we pick because we believe that they can help us discriminate between same source fragments and different source fragments. In the case of glass, we defined 18 features as follows. For each fragment, we took the log of all concentrations and averaged over the replicates to get 18 mean elemental concentrations. And then we constructed pairs of fragments and computed the difference between the mean concentrations for the 18 elements. So these differences are the features that we use to classify the pairs of fragments as being mated or non-mated. So there's a ton of different learning algorithms. There's logistic regression can be thought of as a supervised learning algorithm, support vector machines, random forests, Bayesian classification and regression trees, and many more. In the paper that we wrote, we looked at random forest and Bayesian classification and regression trees. The results were very similar. So in this presentation, I'll just talk about random forests. So the random forests are not difficult to implement, and if you work in R, there's any number of R packages that you can use. But one has to be a little careful. So when there are big imbalances in the training data set, things can go a little haywire. What do I mean by imbalances? I mean, if we have, let's suppose in the case of glass, we have two classes. The class of fragments that have a common source and the class of pairs of fragments that have a different source. If we have many more of one than of the other, then this can affect the performance of the algorithm. So we need to be careful about that. And then the question of independence, or at least almost independence, of the units that are used to train the algorithm and the units that are used to test the algorithms afterwards. So how did we implement the random forest? So we used the data, our data and the BKA data. We mixed it all up. And so we separated the data into a training and validation data set and a testing data set. For the training and validation, we used 28 panes from company A and B, produced on different dates, and all 62 panes from the BKA that came from different sources. So we ended up with 7,700 pairs of mated fragments and over 250,000 pairs of non-mated fragments. And then to test the algorithm, we set aside 20 panes from companies A and B that were produced on different dates, plus the one pane from BKA that had multiple fragments. And so that gave us about 5,600 mated fragments and over 120, almost 124,000 non-mated pairs of fragments. So obviously we have a huge imbalance here. So we have a bazillion more pairs of non-mated fragments than mated fragments. And so we had to do something about that. We used a method called downsampling of the majority class to alleviate the effect of the imbalance. We also used 10-fold validation to decide on the algorithm that we were going to be using to test, that would be tested afterwards on the testing data set. And the errors that we're reporting are just the out-of-bag errors. So there's two types of errors one can get. One is within the training and validation data set, there's an error that the random forest produces. But this is typically an underestimate of the true error rate. And the out-of-bag error, which arises from this testing data set, this is a better, a more realistic estimate of the true classification error. Setting up the comparison between the methods, we had to be a little bit careful about that too. So we only used the testing data set in order to set up the comparison. To implement the two interval-based methods, here's what we did. We selected a question fragment at random from some pane, and then from one of the panes in the testing data set, and averaged the concentrations over the 5 replicates. Then we selected 3 known fragments at random from either the same pane as Q or from a different pane from Q, and averaged the concentrations over the 15 reps, also computed the standard deviations. And then, as I explained before, we computed the standard score and the modified score, as in y-zeral, and then simply counted. We used that score to count how many pairs of fragments were correctly classified and how many were incorrectly classified. For each question fragment, what we did is we randomly selected 30 comparison sets. And so at the end of the study, we had 15,300 comparisons of known mates and over 150,000 comparisons of known non-mates. In the random forest, we make pairwise comparisons. So there were different possibilities here. We could, for example, combine the 3 known fragments into an average fragment. So this would be similar to what the ASTM approach says we should do. And then we end up with 1 average K fragment and 1 Q fragment, no problem. Or we could obtain 3 similarity scores, 1 for each one of the 3 K fragments, and pick one of those 3 similarity scores to do the comparison. For here, I'll show you what happens when you pick the smallest similarity score, which is in principle you think would favor the defense. The thresholds we used were for the interval-based methods. We used the threshold that Drejos and Weiss proposed, the 4. And for the random forest, we use a threshold of 0.5. I should say that the random forest score takes some values between 0 and 1. So here are the results. So here is the first row is random forest when we take the mean of the 3 known fragments. This is the random forest when we pick the minimum of the 3 possible scores. This is the standard ASTM approach, and this is the modified approach proposed in Weiss et al. This is the area under the curve. This is the expected error rates. And you can see the random forest does a whole lot better than definitely the 2 interval approaches, at least in this data set, combining ours and the BKA data. The optimal threshold that one should use turns out to be about 0.6 for the mean random forest approach, about 0.3 when we take the mean, and sort of close to 4 in the ASTM standard, very different when we use the Weiss et al. Approach. This is the false positive rate, and this is the false negative rate. And again, we see that the first approach is the one that does clearly better, at least in terms of minimizing both the false positive and the false negative errors results. Here's an ROC curve, same thing. So here we have the random forest with the mean. Here we have the random forest using the minimum score. Here we have the standard ASTM, and here we have the modified interval method. One of the nice things that the random forest does is it provides a ranking of the importance of the different elements. And so here it's pretty clear that potassium was one of the, potassium, zirconium, titanium, cesium, hafnium, I don't know what this is, Rb, aluminum, iron. These are the elements, probably up to Rb here. These are the elements that were the most important in terms of the random forest to discriminate between mated pairs and non-mated pairs. I think I'm going to skip a few things. I'm going to skip this thing. It turns out that the interval-based methods produce a high proportion of false positives in these data. What is a false positive is the falsely declaring that two fragments are mates when they are not. And why does this happen? This, it turns out it happens because in some elements, the within pane variance is actually larger than the between pane variance. And so when this happens, the intervals get larger, and therefore the chance of declaring that two fragments are indistinguishable also increases. This is just 6 elements. The points here denote the within, let's see, yeah. The points here denote the within pane fragments. These are the panes. And the line, the horizontal line, denotes the between pane fragment. For barium, for example, all of the within pane fragments are smaller than the between pane fragment. Potassium is wonderful. As we expect, the between pane is much higher than the within. But if you look at calcium or magnesium, these are really funny elements. What you find is that the variability within pane is much higher than the variability between pane. And so these elements are really killers for the interval-based approach, because the interval-based, because this, if you look at the intervals for these two elements, they're going to be super wide, mostly because the variability within pane is very high. These are the distributions of the scores you would get using a random forest and using the standard ASTM approach. And so remember, I showed you those hypothetical distributions of scores. At least for this data, this distribution looks pretty good. So among known non-mates, the scores tend to be low. Among mates, the scores tend to be high. And so in principle, you could separate pretty well mated from non-mated pairs of fragments. We looked at many other things. This is very fast. Again, I'll skip. But we tried to see whether we could improve the standard approaches if we increase the number of control fragments. And for the standard ASTM approach, you can decrease the false negatives quite a bit. But the false positives stay pretty constant. Why is that the case? Because of that floor that we have in the standard deviation. So what happens is that when the variability, you cannot go below 3% of the mean in terms of the standard deviation. So the effect of increasing the number of controls doesn't do a whole lot for you. In the case of the modified for sigma criterion, increasing the number of controls does absolutely nothing. You might improve the estimation of the mean concentrations, but since you're using a fixed standard deviation, fixed relative standard deviation, it doesn't matter how many control fragments you might have. What happens when we compare fragments that were produced 1 day apart, 2 days apart, 3 days apart, 12 days apart, 15 days apart? This is the proportion of incorrect decisions that is made by the random forest and by the standard ASTM. Obviously, when you have paints that are manufactured one day apart, those are hard to tell apart. And so you make more incorrect decisions. By the time you look at fragments that were manufactured 8 or 10 days apart or 12 days apart, then the random forest is making very, very few incorrect decisions. And the standard approach is making fewer incorrect decisions as well. So here's some final thoughts. We think it's possible to do better than the current standards. There are no data out there, and little progress will happen until more data become publicly available. We realize it's expensive to get this time data, so the data that we make public, we're not publishing the device data, those data are not ours, we're just publishing our data. And we spent over $50,000 collecting those data. And so it's not trivial to get this data, but one should try. Not sharing data impedes progress. We were very disappointed. We contacted Dorn to see whether we could get the data that Dorn and collaborators used in the 2015 paper, and we were denied access to those data. From a statistical point of view, and I realize this is not a popular statement among glass examiners, the problem is similar to the bullet-lead problem in the following sense. What do we really mean by same source? It's difficult when you have this continuing production process to determine what we mean by same source. Do we mean the same window? Do we mean the same day of production? What is it that we mean by same source? And a related question is it possible to draw conclusions beyond I cannot exclude this broken glass at the crime scene from being the source of these fragments I found on the suspect? Is it going to be ever possible to identify the exact source from what that fragment came? I'm not sure. I think that one conclusion is that the interpretation sections, sections 10 or 11, I don't remember, in both of the ASTM standards are premature. And when those arguments are presented to lay persons that do not understand all these intricacies, I think those interpretations can be misleading. Thank you for your attention, and we're open to questions. I have the fan base here. From Paul to everyone, what is this soup in the background? What soup?
Everything is soup.
Oh. We don't know. No questions? Oh, finally, Jeff. Okay, this is, so I don't know if everybody can read, but it says using a supervised technique seems like it could have the danger of allowing the algorithm to exploit empirical data that are actually just noise. I'm confident that your math is correct, but I'm concerned that the chemistry might be wrong. The similarity score shouldn't be too shrouded. It is ultimately based on concentrations of the measured trace elements. So, okay, yes, so one of the problems, one of the big problems of learning algorithms is that you can overfit. And what does overfit mean is, means that you are not only using real differences in the features, but also noise in the data to train your algorithm. So this is why it's very important to have very good and very extensive training data, and to make sure that you're testing your algorithm on a data set that's independent of the one you use to train the algorithm. The math is correct. I should have said that we tried before we even got started with anything, we tried to reproduce the results in Weiss et al. We reproduced all the results exactly. In fact, we found a small mistake in one of the tables. So we know we are applying those methods correctly to the new data set. I'm not understanding the chemistry statement, Jeff. So maybe while I answer to Philip, you can explain that better. How do you decide which order to put them in? Oh, I see. So when you take the difference between the two fragments, so do you take Q minus K or K minus Q is what you're asking? It really doesn't matter. The score, the interval-based score takes the absolute value of the difference. So it's just the magnitude of the difference, not the direction. Did I answer that one? Oh, did you calculate the empirical cross entropy of the score method? No. What do you mean by empirical cross entropy of the score method? Do we know?
I can see the paper.
Okay.
There's a lot in like biometrics.
Oh, okay. No, we didn't. But thank you for the suggestion. Oh, it's a measure of the performance. Okay. Now, we only measured performance in terms of classification performance. That's, I hope I made that clear. So that's all we're doing here. From Cedric, the score method is a decision method. It does not, no, that's absolutely true. Did I say probability? The score method, huh? Sorry? Oh, I see. Okay, let's see. Joanne, what do you use to determine the variability between pairs of elements? There was a flat line on your charts. The between pair variability should be related to the concentration of elements. Oh yeah, so okay, let me see. Can I go back? Well, okay, so in those charts, what I showed was two sources of variability, right? The dots were the within pane variability, so the variability between fragments within a pane. And then the flat line was the variability across all the panes. So you only get one estimate of that because you have, you compute the variance across all panes, right? And so that was what that flat line was. And then that was just to provide a visual comparison of the within to the between variability in those elements. Jeff says, my chemistry statement is related to the overfit problem. Your slide shows the seemingly most important elements might be unique to each Q and K. I think we should talk about this offline because I don't know. Does anybody understand what Jeff is saying? I think we're a little bit at a loss, Jeff. Can we talk offline about this? Roy Maxian, can you say more about how the work is critically dependent on the data? Yeah, sure. So, I mean, when you have a random forest, essentially what you're computing is a classification rule. And so if I have a classification rule that works for this very small data set, and then I try to apply that classification rule to a pair of items that have very different properties from the ones I use to compute the classification rule, then I'm going to get, the classification rule is going to fail. And so I need to train the algorithm on the data that let's see, if I know that I'm going to be using this algorithm to classify fragments from containers, for example, into same container, different container, then I must train my algorithm on a very large number of pairs of fragments from containers, so that, when my algorithm views this new pair of fragments, it understands, right, that this new pair of fragments is similar to the one the algorithm saw before. And so that's what I mean in terms of dependence on the data. What else did it say? I've missed one. Oh, no. Okay, thank you, Cedric. I didn't say probability. All right. Oh, thank you. Okay, good to know. Roy, again, how do you know at the outset that the data are okay? Well, that's $1 million question, right? So you don't. And so and this is something that one needs to think about much, much more carefully. I suppose I envision a day. Imagine that you have, instead of having data from 2 manufacturers and the German data, imagine we had data from all the major manufacturers in the United States, and over time, so data that were collected this year and next year and the following year. And we had trained our algorithm on that. So that data set would be much more appropriate, if you will, than the one we had, which was limited to 2 manufacturers and 1 month in 2017. And so I would imagine that at some point, you would not be getting data that are too terribly different anymore. So unless glass manufacturers change their production methods, you would expect that at some point, you're going to start seeing the same concentrations and the same arrangement over and over again, so that even if you keep updating the data, the distributions of scores, the reference distributions of similarity scores might not vary anymore. And so if that were ever the case, then I'd say you probably have the data you need. Offline is good, great. From Hal, do you have a sense for what would happen if you train validate on A only and then test on B? If you take your current classifier and apply it to data from a new manufacturer, you would try that? No, I am imagining that it would fail miserably. Would you think? We don't know. We'll try. We did try. Let's see. Did we train our algorithm on our data and use it on the BKA data? We did some of that.
In the sense that we are training the random forest, only the difference for the mated and non-mated.
Yeah.
So still, if the test data is from the company B, we might do good.
Yeah, because that's right. So Young has a very good point, because what we're looking at is differences in elemental concentrations among mates and non-mates. And so you would expect that the differences between mates from company B are small, just as they are in company A. And you would expect that the differences in elemental concentrations among non-mates are going to be larger, just like they are in company A. And so the actual mean concentrations are very different, but maybe the differences in the concentrations among fragments from same source and from different source are the same. So I think that would, who knows? I think it might work, yes. Did you try to train on BKA data and test on BKA data? The problem with the BKA data is that it only has one pane that provides information about same source. So we didn't, if we used that one pane to train, we didn't have anything to test on. And so those data are just not extensive enough to do any of this. Jonas from Sweden again. What problems does the mate-non-mate imbalance give? My refractive index data looks similarly imbalanced. So you end up with a bias classification rule. So the difference is, in our case, the majority class was among non-mates. And so the problem is that those are the ones that dominate the learning of the algorithm. And so you end up with not the best classification group. Welcome. What time is it in Sweden? Mm-hmm. 21 p.m. Okay. 9 p.m. Isn't analyzing data coming from crime scene a little bit sad? Huh? Yeah, I guess so. Yes, I know. I know. It could be a burglary, right? Right. It's because I feel a little bit down. Well, Paul, forensics may not be for you. I understand, but maybe I need to go. We'll see. Other questions? Thanks, Yuchia. Okay, the presentation is going to be available on the CSAFE website, which is www.forensicstats.org. And I don't know, within the next couple of days, within the next day or two, it should be available. And we can also upload it to the repository. So we'll put it up on the GitHub repository as well. So if anybody uses the data that we are uploading, we'd love to hear from you and see what you find. We are hoping to get more funding to continue adding to those data. So we have fragments from other manufacturers that we haven't analyzed yet, but we will. And it would be great to go back to the same manufacturers and get more data a year later to see what the temporal variability is. So unless anybody has anything burning, it's 3 minutes past the hour. Thank you for listening to us. And bye-bye to everybody. Don't miss the next webinars. If you have any more questions, contact either one of us. Bye-bye.